Pierre-Adrien, please. See your time.
Yes. Can you hear me and see my screen?
Yes, great.
Perfect.
Great. Don't see anything on the screen, but it looks like it will show up right now. To expand it a little bit, it would be great.
So and now is it okay?
No, nothing. Click on the first slide. Expand. We'll see you, but okay.
Okay, technical issue. Is it okay?
Mm-mm.
I think I at least I can see the slide.
Well, yes. There is
Okay.
not full screen, but I think it's okay. I think if you click on the first slide, it will expand to full screen. Yes, great.
Okay. So thank you for the introduction. So this session is about induced superconductivity, but my talk will not be about superconductivity. It will be talking about one of our ongoing projects, which is a collaboration between experimentalists in Lund University in the south of Sweden and theoretician from Uppsala University in the north of Sweden. So namely the group of Ole Eriksson and Oskar Grenos. And we are working on understanding the ultrafast dynamic of tantalum disulfide. And tantalum disulfide, to understand its physics, the main phenomena that rule the physics of this material is charge density waves. So charge density wave, the best way to understand them is to consider one-dimensional metal. And so in a one-dimensional metal at low temperature, electrons are going to fill the parabolic band until the Fermi level. And this state of matter is in fact not the most energetically favorable state. The formation of a periodicity with a wave vector corresponding to the Fermi surface will lead to the bandgap opening, which is going to reduce the energy of the electronic structure. And this reduction in the electronic structure energy is often more advantageous than the cost of reorganizing the lattice. So in general, at low temperature in a one-dimensional metal, you will have a charge density wave, so a non-homogeneous density of charges accompanied with a periodic lattice distortion. In 2D materials, such as tantalum disulfide and a few other transition metal dichalcogenide, you will have also some similar effects, so non-homogeneous density of charges accompanied by a lattice deformation. And so you will have the formation of a polaron, the so-called Star of David shape. And inside you will have so 13 tantalum atoms, each contributing one electron. And so this single electron in the center will follow the Hubbard model that was described at length in the previous talk. So I will not go too much in detail inside this model, but basically it's just you have a competition between on-site repulsion and hopping. And this will lead at a sufficiently low temperature to the appearance of a Mott insulator. And this is this Mott insulator that is ruling the rich physics of this tantalum disulfide. So among the interesting phenomena of this material, there's a really rich phase diagram with many charge density wave state with a different degree of commensuration from incommensurate to fully commensurate. Additionally, there has been demonstration in the seminal paper by the group of Dragan Mihailovic of the existence of a hidden phase of this material. Upon doping and pressure, superconductivity appear. And what is interesting is that superconductivity only appear starting from phases that are discommensurate. And finally, since you have a Mott insulator, you can also have a magnetic frustration. And this material has been proposed as a potential candidate for a quantum spin liquid. But in our work, we are trying to focus, first of all, on this room temperature nearly commensurate charge density wave. And so in this phase, you will have the formation of a domain of a Star of David cluster. And this domain will be surrounded by a metallic discommensuration, metallic domain wall. So what is interesting about this material, or what is still not well understood, is what are the properties per se. For example, you have some metal type of behavior. The dynamic of this material, the ultrafast dynamic, shows some metallic behavior. However, if you look at the temperature dependence of the resistivity, it have more of a semiconductor type of a temperature dependence. Similarly, there has been demonstration of the existence of hidden phase or metastable phase driven from the commensurate phase. There has been some report of a metastable phase driven from the early commensurate, but these are scarce report. And finally, there's like I mentioned previously, the link between this material and superconductivity only exists in phase with discommensuration. So these are main open questions remaining in this material. But here we are going to mainly focus on these two first open questions. And so in my presentation, I will first briefly, since most of you are well-versed in ultrafast technique, I will just briefly skim through the experimental setup we used. And then we perform experiment on the quasi-particle dynamics using ultrafast pump probe spectroscopy, visible pump probe spectroscopy, with the idea of trying to unify, since this material has been studied with really a lot of technique, time resolved RPS, X-ray electron, which can interrogate individually either the electronic system or the lattice system. We wanted to use optical pump probe spectroscopy to kind of create a unified picture with all these different techniques. And in a second part, I will talk about the collective dynamic or the coherent dynamic, and our work demonstrates the evidence of a new metastable phase that is driven from the nearly commensurate charge density wave phase. So first, ultrafast spectroscopy, like I mentioned in my first slide, charge density wave are often associated with a periodic lattice distortion. So it's difficult to separate the response from the electronic system and the lattice. And so that's for this reason people are using ultrafast spectroscopy, because when you excite your system, you are going to have a series of events that are going to occur. And usually the electronic system will respond on a much faster timescale from the lattice, so we are able to dissociate these two responses. So to do that, we use the classical pump probe spectroscopy. So I will not go into details since you are all specialists of that. I will just show you a quick video as a promotion for Sweden. So if you have the occasion to come to Sweden, I highly recommend you to go visit the Nobel Museum, and you can see this display that was offered by Ahmed Zewail when he received his Nobel Prize to explain the concept of pump probe spectroscopy and how we can study some phenomena with such a high temporal resolution. And so with pump probe spectroscopy, we can at the same time track the electronic response and the coherent lattice response. So here is an example in a single crystal of a perovskite material. So we wanted to understand the quasi-particle dynamics of a tantalum disulfide, and most of all, we wanted to have a coherent picture, unified picture with all the diffraction and photoemission spectroscopy technique. So as I mentioned in the beginning of my talk, the early commensurate charge density wave phase have a resistivity that increase when we decrease the temperature. So this is kind of typical of a semiconductor material. On the other hand, if we look at the RPS data or transient reflectivity on a short time scale, the decay can be pretty well modeled with a two-temperature model, where first we drop energy in the electronic system, and the energy is going to go into the lattice through electron-phonon scattering. So we perform a pump probe experiment with a wide range of pump wavelengths and also probe wavelengths, and we use the single wavelengths or white light continuum. And if we look at the early time scale, we can indeed model quite well our dynamic with a two-temperature model, where we first excite the electron and they decay exponentially by giving their energy to the lattice. And on the longer time scale, heat will dissipate through diffusion. But if we look at the larger time scale, we see some discrepancy with this model. Namely, we see still this fast decay on early time scale, but we consistently, no matter what is our pump wavelengths or probe wavelengths, we see a rise on a few picosecond time scale. And finally, on longer time scale, we see this long living background. So we were quite wondering how to explain this model, because a two-temperature model will not be able to explain a reflectivity rise for a wide range of wavelengths. So you can see here, for example, we try to model with a two-temperature model classical of a metal on the from few femtosecond to 100 picosecond, and we are not able to reproduce our data. In order to reproduce our data, we used a model that consider 4 decay processes. And if we separate these decay processes, we obtain a form timescale. And what is interesting is that the metal model fits our data really well at the early timescale, so which is kind of a classical timescale for this electron phonon process. And on the longer timescale, we also see a good agreement, and this often corresponds to the heat diffusion. Now the question is, what is the origin of this 1.4 picosecond and 4 picosecond signal? And what is important is that the 1.4 picosecond is a positive change of reflectivity, while the other, the 4 picosecond is a negative. So this kind of, if we consider that the reflectee is in fact tracking the temperature of the electron bath, that would mean that this 1.4 picosecond is a relaxation process, while this mechanism will be something that will increase the temperature of the electronic system. So first of all, if we look at the band structure of our material, in the undistorted phase, so in the discommensuration, the particularity of this tantalum disulfide and other transition metal dichalcogenides is that there is a band that is straddling the Fermi level. So when we excite with our pump, we are going to generate electrons from this sulfur dominant orbital into some tantalum orbital. And when electrons are going to relax through electron phonon coupling, they are going to accumulate at this M point, which is the lower part of this band that is straddling the Fermi level. On the other hand, the hole will be predominantly accumulating at the gamma point. And so that means that in order to have electron-hole recombination, we need to have interaction with a phonon, emission or absorption. And so this is our 1.4 picosecond time scale will correspond, in fact, to this electron-hole recombination mediated by phonon. And if we look at material with similar band structure, so bismuth is a semi-metal where the top of the valence band and the minimum of the conduction band are not located in similar area of the Brillouin zone, then we obtain some similar type of a time scale. Now, considering the 4 picosecond time scale, the one that seems to imply that there is a rise in the electronic temperature of the material, to understand this contribution, we need to look into the different part of the material. Indeed, there's some discommensuration that will have a specific band structure with a band that is straddling the Fermi level. But in the distorted part, in the star of David, there will be the opening of a gap due to this charge density wave between the K and the M point. So right in this region. And so what has been shown is that when a femtosecond pulse is absorbed, that has been shown with a time resolved RPS, then this gap is going to close due to electron phonon coupling. So on a time scale of the electron phonon coupling, like we have seen a few hundred femtoseconds in this material, we are going to close this gap. So if we look at the dynamic that we expect when we are going to photoexcite electron, we are going to have electron relaxation through electron phonon coupling and a relaxation and the closing of the gap. So electrons are going to be able to relax inside this state. But when the gap is going to reopen, this state are going to disappear and electrons are going to be pushed to higher energy. And so what we see in our experiment is that these electrons are going to be pushed on a time scale of 4 picoseconds. That's what we have observed. But if we compare this result with what have been observed with electron diffraction and X-ray diffraction, the re-establishment of the charge density wave gap takes this 4 picoseconds. So we have built a complete picture of the dynamic inside this material. So first, our pump is going to excite electron from this sulfur band to tantalum band. Then through electron phonon, we are going to have a melting of the charge density wave order. And at the same time, electrons are going to accumulate at the M point and hole at the gamma point. They are going to recombine through electron-hole recombination. And this is kind of really one of the first time that this mechanism is observed in this tantalum disulfide, but it could be also applied to tantalum diselenide that also have similar type of a band that is not crossing with other valence band. And then on a longer time scale, we will have reestablishment of the charge density wave that is going to create a gap, and finally heat diffusion on a nanosecond time scale. So we have rebuilt the whole dynamic of the tantalum disulfide in this nearly commensurate charge density wave phase, and we have been able to get a unified picture with time resolved RPS that is really sensitive to the electronic structure, and XRD, time resolved XRD, and electron diffraction that are sensitive to the lattice. So in the second project, we are caring more about the collective dynamic or the coherent dynamic. And this is all stemming from this paper where they demonstrated that through the absorption of a femtosecond pulse, the system can be driven into a hidden phase. And one of this signature, one of the main results of this paper is that phase can be characterized in charge density wave by their vibrational spectra. So with this in mind, we have been interested into a recent result using electron diffraction, where they predict the existence of a hidden phase that can be driven by photoexcitation using from the nearly commensurate phase. So our idea is to try to see if this hidden phase can have a different vibrational signature than the nearly commensurate phase. So we first started to do an experiment at low pump power in order to avoid driving the system in this potential metastable state. And we obtained a beautiful coherent oscillation. And when we perform the spectra, we can see that it's composed of multiple vibration. By comparing to Raman data, we were able to attribute this mode to either zone folded phonon. Indeed, when you have this formation of the Star of David, you are going to have additional periodicity, and you will have a folding of the acoustic dispersion relation that are going to lead to some zone folded phonon. And there's also this amplitude mode that are softening when we increase the temperature and getting closer to the phase transition, and that are representative of the charge density wave inside the material. So we performed experiments with increasing pump power. So from this regime where we are at extremely low density of photo-excited electron to really high power. And what we can observe is that there's a strong variation of the oscillation when we increase this power. So we can see that the lifetime seems to be shortening, and we also see that this structure seems to disappear and leave place to another type of oscillating pattern. If we perform the Fourier transform, we can see similar effect where this two amplitude mode, especially the one at 3.6 terahertz, kind of disappear almost to become an anti-resonance or phanoresonance for that matter. So what we perform to understand this better is a time frequency analysis from this signal. So at low power, we see what I presented previously. So these two dominant amplitude mode, and we can also observe at 3.1 and 1.9, we can see this zone folded phonon. But when we increase the power, we start to see the appearance of a phonon mode at higher frequency, and we can see that the 3.6 terahertz mode seems to disappear and reappear at a higher time scale. And this is even more observable on at higher power, where there's almost no contribution of the 3.6 terahertz until 1 picosecond, and the signal at early time scale is dominated by a vibration at 4.5 terahertz. So if the vibration of the amplitude mode is a signature of the phase of the material, we have here a change of this vibration spectrum, which indicate a change of phase and the existence of a metastable phase that disappear in a 1 picosecond time scale. And what is interesting here is what is the origin of this phase transition? Namely, is it a thermally induced transition, or it is some type of photodoping effect? So what we performed is we modeled our the two vibration at the high frequency at 4.5 terahertz and the low frequency at 3.6 terahertz, and we compare the amplitude of both. And the idea is that if it's a photodoping effect, we should be able to see that the relative amplitude of these two contributions will depend on the density of photoexcited carrier inside a layer. And so when we apply more power, then we should have a bigger part of the sample that exhibits this phase transition. So with this model in mind, this little model in mind, we can model the relative amplitude of both contribution using this model, and we can extract a critical density of photoexcited carrier that will lead to this phase transition. So we extracted a critical density of photoexcited carrier that is roughly 5⁻⁻² electron per nanometer cube. And if we compare to this proposed hidden phase from the nearly commensurate at 300K, we have some critical photodensity that is quite similar. So overall, I have presented a complete picture of the relaxation dynamic. We highlighted the fact that dynamic is the relaxation is experience a bottleneck due to phonon-mediated recombination, due to the fact that the band that is at the Fermi level doesn't intersect with any of the valence band. And this is particularly interesting because the center, the phonon that are required in order to do the recombination are phonon linking with large momentum from the gamma to the M point. And when we cool down at temperature, these phonons are going to be less populated, which could explain some the long lifetime of the photo-induced hidden state of tantalum disulfide. So we also observe the charge density wave quench and reestablishment inside the transient reflectivity. And what is nice is that our results are at the same time coherent with the RPES data and also techniques that are more sensitive to electron dynamic, such like to lattice dynamics, such as X-ray and electron diffraction. The second project concerned the existence of a photo-induced metastable phase from the nearly commensurate phase. And so we were able to demonstrate that the vibrational spectrum of a phase is really a signature of this phase. So we can use this as a probe of a phase transition, like has been done in previous experiment. And we highlighted the existence of a metastable phase that have a lifetime of few picoseconds at a few hundreds of femtoseconds at room temperature, in agreement with the predicted existence of a phase that can be driven from the nearly commensurate charge density wave. So with that, I would like to thank my collaborators, so Professor Kardigatsev from Lund University for the experimental side, and also the group of Professor Eriksson and Grones at Uppsala University, and my funding agency. Thank you very much.
Thank you, Pierre-Adrien. Questions, please. Okay. Thank you very much. Thank you again.